Sorry, Gabe.
Oh, you're good.
Cool. So, howdy, Dan. Hello. Some new stuff that kind of ties everything that we've been doing with the end of the semester. So, like, this is a link right here between the first half of class and the second half. We'll come back to this in a bit, and it'll be very important to us. We're gonna talk about improper integrals. All right, so what is an improper integral? All right, so here's the problem. Let's say I've got y equals, let's do this as an area problem to kind of understand it. Y equals 1 over x squared. That looks like this. At least for the positive x, it actually looks like this over here as well. What if I wanted to find the area from 1 all the way down forevermore, and that never ends? That's an asymptote, right? So this is asymptotic behavior here. And what if I wanted to find this area? So find the area of this unbounded region. First off, we don't even know if that's possible, right? It could be an infinite area. We don't know yet. We're going to know how to do this in probably about 15 minutes. So here's the plan. We're going to find the integral for a finite region. So we're gonna make the problem a little simpler first. So this is still 1 over x squared. I'm going to go from 1 to b. So I'm going to do this finite integral. So step 1 is deal with a finite region first. So I'm going to find that area here. So I'll call this little area, it's like area sub b, something like that. And that area of b is going to be the integral from 0 to b of 1 over x squared. We've been doing this like crazy. That should not be, well, there you go. Adios, eraser. Let me know if that makes sense, what I'm talking about. So like the ideas aren't going to be heavy, really. You understand the heart of the problem, as long as you understand what I'm saying here. Does this look good? So I'm gonna crank that out. So find the area formula. Notice the formula is going to depend on b. So that's going to be, let's see here, so this is integral 1 to b, x to the negative second dx. So I'm going to take the antiderivative, that's negative 1, x to the negative first. I'm going to evaluate that from 1 to b. And so this is just 1 over x, that's negative 1 over b minus negative 1 over 1. And what I got is positive 1 minus 1 over b. Stop for a second. That's the area of this little piece right here. So now we understand this region, no matter what b is. What do you think I want to do to that answer if I'm actually interested in this area here? Like that goes all the way out, never ending. Absolutely. We're going to take the limit on that area, right? So for each fixed value of b, when b equals 1, the area is 0. That makes sense. When b equals 2, the area is a half. When b equals 3, the area is 1 minus a third, 2/3. So to find the true area, to find the total original area, we're going to take, just like Voin said, the limit as b goes to infinity. of this answer. And what do I get for that? So what is the limit of that? What is the limit of 1 minus 1 over b as b goes to infinity? 1. 1. How'd you get that? That's right.
Because anything divided by infinity is 0.
Beautiful. So let's check this out. Here's like kind of one of the fundamental rules to remember for all of this. When I'm taking limits at infinity, what you're basically assuming is that b is becoming larger and larger. And Voigt's kind of like doing this mnemonic way of saying, oh, I'm going to put infinity in for b. And that can work a lot of the time. Here it definitely works. This is the only moving part. So this is the part that's moving. The top is fixed, and the bottom is blowing up. In other words, getting bigger and bigger. When you have something like this, that goes to 0. And that is a key fact. You got a fixed top, bottom blowing up, you're going to 0. Keep that in mind, because it's going to happen over and over and over again. So this limit here is then going to be just 1 minus 0, or 1. This actually has a finite area. This region right here has a total area of 1, even though it's unbounded. So this is a really kind of crazy idea. It's a very mathy thing. I've got a region that is infinite in size, but finite in area. That's weird, but it's part of our life in Calc 2. Does this process make some sense, what has just happened here? All right, so let's look at the process in general. So in general, to find, and here, so I'm going to write some new notation here. Let's say I have an integral with infinity as the upper limit. And we've got some lower limit down here. This is some fixed quantity. Could be 0, there it was 1, could be all sorts of other numbers. This is the thing that makes this integral improper, that infinite limit. And then I've got f of x dx. Step 1 is replace the infinity with a variable. So replace infinity with a variable. I'm going to use b here just because I used a for the bottom and b like kind of the classic on top thing. Do that. Find this integral. Work this through and you'll get a formula in b. And now out in front, we're going to write limit as b goes to infinity. So I've taken the infinity off as a limit, put it out front as a process to happen at the end of all of this. But otherwise, it's just regular old calc like we've been doing, and then I take a limit at the end. So the way to do this is find the definite integral, then take the limit. Let's do a couple together. So could you, my friends, find this one? So we're going to do, let's give you the integral. Integral from 2 to infinity of 1 over x cubed dx. Please find that. Step 1, let me get you rolling. Step 1 is replace infinity with b. Might want to rewrite that x. Let's crank that out together. See what we get. I'll draw a picture of what we're finding. I imagine Friday's Zoom class will be us getting together and working on some of these problems together. So we can talk, have emotional support, all that stuff, and mathematical support, I guess. So gosh, I don't know what the answer. Anybody get a quarter? Is that what the answer is? No. 3/4? Shit, I don't know. Maybe I just do it instead of just guessing, I guess. Half? Is it half? What you got? What you get? It is 1/8. Let's see. Oh, because of the, yep, the 8. I forgot about the 2 that came out like that. When you're writing this stuff out, you kind of want to keep that limit coming along to remind you to do it. Mostly, why did I put 0A there? I meant 2. See if we're syncing up how we're thinking about this. Anybody want to talk about anything up to this point? Haven't done the limit yet.
Would you just be able to just go over your work?
Yeah, absolutely. Cool. So how about from here to here? Does this need a little talking?
No, from, that to the last one.
Let's stay here. Okay, cool. Yeah, so here I just did the power rule. And then when I went down to here, I plugged in the B. And what I'm doing is, in my head, I'm realizing that this thing here, Gabe, is actually this. So that's just this.
Oh, yeah. Okay.
And so when I put in the B, then I got that. And then when I put in the 2, I got the negative
okay.
and 8.
Okay, got it.
Does that help?
Yeah.
Yeah,
Thank
awesome.
you.
What's this limit as B goes to infinity? 0. We use Voigt's rule, right? Voigt's theorem. So the top is fixed, bottom is blowing up, goes to 0. That's like the sweetest limits at infinity ever. You got that fixed top. It's when that top isn't fixed that things get weird. But for right now, the area of that thing is just 1/8 units squared, whatever the unit is. And again, we have an infinitely large region that has a finite area. How interesting and strange.
Can you explain the -1/2x
I
where you
totally-
just replace the b with x?
This right here?
Mm-hmm.
Yeah, so are you cool with getting to this point, Sophie?
Yeah, I'm just confused how you went from the -1/2b squared and then.
Gotcha, so this quantity here, so the x to the -2 is 1/x squared.
Right, yeah, that I get. It's the down below one that I'm confused with. The one right by your right hand. Down.
So this here?
No, down. That one.
Oh, well, I mean, there was just a -2 in the bottom already. So, right, I was taking this thing here, where I had x to the -2 divided by -2, and I just copied that -2 over.
Just because it's -1/2 times x to the
That's a
-2.
good way to think of it as well.
So you're substituting the x back in for b. Where did the b go?
Oh, here?
Yeah.
So the b, so I took the limit here. So let's stop. Without the limit, are you cool with this? Let's try to diagnose. Are you without the
Yeah,
limit?
no, I have no, yeah, I'm good there.
Okay, awesome, cool. So here I took the limit then. Now I'm gonna let b go to infinity, and this quantity is a fixed thing, that's a 1, over something that's becoming bigger and bigger, right? I've got 2b squared, so when b is big, this thing's even bigger, right? So I've got big squared in the bottom here. There's also a -2, but key thing is this quantity is becoming smaller and smaller in magnitude as b gets bigger and bigger. So what I'm doing is this. I'm taking the limit as b goes to infinity. Let's pull that 2 out. Look at that quantity. Do you see that that is 0?
Mhm.
So that's all I'm doing here. I'm just saying, oh, this thing dies as b goes to infinity. The -1/2 out in front doesn't change anything. Right, I can put that up in front like this.
Okay.
Are you sure?
Well, I guess I just don't understand then if that dies and goes to 0, then what is the -1/2x squared? Where did that come from?
Oh, so this was just me writing as a side note, sorry.
Oh.
Okay.
I was gonna
We
say,
could have
I'm
fixed
like,
that
I
up
feel like
earlier.
I'm going insane.
Yeah, that was me like just talking through how this became this.
Oh, okay. That's okay.
Oh, I see now.
Yeah, I.
Got ya, okay.
Okay.
It was the extraneous math.
Mhm.
Okay. Other questions on this? I got one more for you. I got 2 more for you. Could you do this one? So we've got integral from 1 to infinity of 1/x dx. Could do that one, please. And then one more. That one too. Can we do both those? And then we'll summarize. We'll see something. We'll talk about the thing and have a nice little rule. Go grab some water. See what folks are doing first on this before I give it all away. That looks good. That looks very good. Yeah, I'm seeing good stuff. I'm seeing good calc. It's just those limits are going to be tricky, maybe. Yeah, definitely. Yeah, you got it. Looking good. Just gotta get those limits out. Might want to look at a graph. Graph might help because, yeah, it's tricky. If you don't have a picture of natural log in your head, the first one could be these looking? Are we agreeing on the computational aspects of this? What is this limit? Positive infinity. If we pull out a graph of natural log, looks like this. Good thing to be able to reproduce. So if this is x, this is natural log of x. We know that natural log of 1 is 0. There's all sorts of things I can suss out from just looking at this. So first off, let's check here that the limit as x goes to infinity of natural log is infinity. It just keeps growing. But there's also another really cool fact that is a little less obvious, and that is the limit as x goes to 0 from the right. Remember how this, so we're going to talk about limits, kind of gentle introduction here. But this means x is approaching 0 from the right. It has to, because natural log isn't defined on the left of 0. Of natural log of x is negative infinity. We shoot down. So I can take a look at this graph and grab both those facts from that. Good facts to know. So this is actually infinite. That's infinity. We say that the integral is divergent when I don't get a finite number here. So this integral is divergent. So we don't get a finite value. Next one, what is this one? How does this limit roll? Somebody besides Voin tell me this, because I know Voin's going to tell me if I just ask it out there. What's this one?
It's still infinity, isn't it?
It sure is, Abraham, because this is a square root function, and that looks a lot like natural log. So this is square root of x to x. What's the square root of 1 billion? Big ass number. What's the square root of 10 billion? An even bigger ass number. So this quantity grows without bound, and the answer is infinity here. Infinity minus 2, still infinity, big. So one thing to keep in mind is infinity is a process in a way. It's a place we aspire to. It's never a place we can get. So when we write this, we just means grows without bound is really the way to say this.
Is that why we don't need to put the minus 2 in?
That is correct, yes. So I wouldn't, yeah, exactly. Once you've got like infinity, if it's plus or minus anything finite, that's a good question, Sophie. That's just infinity.
So the square root of infinity is just infinity.
It is. It is. But we don't want to get crazy. I think now you got me excited, Abraham. So excited I'm scooting. I don't want to think that anything, if I start thinking things like this, I might get into trouble. Because I might start doing stuff like canceling infinities, right? And then I would have something insane like that. But it's fun to think about. But yeah, infinity squared is infinity. And the square root of infinity is infinity. So we can kind of intuit that. We just don't want to write it. It's a secret inside. Any questions on those? Because I want to sum up what we just saw. Some crazy stuff, actually. Notice that. Let's just, in summary, this was finite. This, I think I had a cubed, right? Yeah? This was finite. And we had a 2 here or something like that. This was infinite. This was infinite. But all those curves look the same. Like if I gave you a curve, so all these curves, 1 over x squared, in other words, y equals 1 over x to the n. If I sketch that out, they all go through 1, 1. They all go down asymptotically to 0 as x gets bigger. They all look like this. What is happening is that this power here, as it gets up above 1, so right now, 1 over x is the dividing line. if I have 1 over x to any power higher than 1, so like right down here, this would be like 1 over x squared. This is 1 over x cubed. They die off fast enough that the area can be finite. They die off so fast that the area actually can add up. Whereas at 1 over x, that area will not be finite. That area is infinite. But even this, if I gave you this integral, if I said, what is the integral of 1 over x to the 1 point, that integral is finite. Let me prove it to you really quick. Let's see, how many damn zeros I got here? 1, 2, 3, 4, 7, 8, 9, 10, 11. It's 11 zeros. I don't even know what that number would be called. But if I work this through, and I like to show everybody this because it's kind of a cool 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Damn. Dx. Let's work it through, keep the limit out in front. Add 1 to that, and what we get is x to the negative 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, over the new exponent, negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Boom. Going to do that from 1 to b. Let's keep doing it. Let's finish it up here. So this turns into, now I'm going to put the b's in. I got limit as b goes to infinity. When I put b in first, look at what I'm going to get. I'm going to get negative, or 1 over negative 0. That times 1 over b to the positive exponent 0.0. There's supposed to be 11 zeros in there. There may or may not be. And then minus, put in the 1. So I get minus negative 1 over 0.1. I could have probably had less zeros in there and gotten the point across, but we get that. So take your limit. Here I've got 1 over something that is blowing up super slowly. But it's a positive exponent, so the bigger b gets, the bigger this b to that power gets. So this thing here still goes to 0. If I have the limit, let me just give you a nice little rule. If I have the limit of b goes to infinity of 1 over b to a positive number, that's 0. Doesn't matter what that number is. Then I'm left with a plus piece here. So this piece dies, and I'm left with positive 1 over 0.4, 5, 6, 7, 8, 9, 10, 11. Shit. What is that number? It's a big ass number, right? It's 1 divided by whatever that is down there. And I think it's, let's see, if we divide 1 by 100th, we get 100. So it's a 1 with 12 zeros. That's the area. Under, what the hell was the curve to begin with? Where is my problem? Oh, down here. This guy right here. So that curve, here's 1 over x. Here's the curve that we are looking at. And the area underneath that thing is finite. It's huge, but it's finite. And the closer this, and the more zeros, and you can probably believe this now, the more zeros I insert here, the more zeros I'm going to have pop out on my answer at the end. Put another 0 inside here, get another 0 out. So the closer this thing gets to 1, the bigger the answer is, but it's still always finite. So what I'm trying to say is this. Let me sum it up. What I'm trying to say, and it's a good rule of thumb, is if I have this integral of 1 over x to the nth power dx, that is finite. if n is bigger than 1. The minute that's bigger than 1, this thing becomes finite. If this number down here, if n is 1, it's infinite. If n is equal to 1 or greater than 1, or excuse me, or less than 1. So less than or equal to 1. Less than 1 was like the square root. I got 1 over square root, like we saw. That was infinite. So the fancy term for this is, this integral converges if n is bigger than 1. Converge means it hits a finite value. The limit exists. And it diverges otherwise. Great rule to know. And in fact, you could put any, it doesn't have to be 1 down here. Here's any finite number down here. Put any finite number you want down there. That integral has that property. So then you can knock stuff out really fast. You could look at this and go, diverges, because n is 1/2 there. Converges, converges, because the exponent is bigger than 1. If I gave you this problem, what's n there? What's the n exponent? 1/3. So here n is 1/3. This is x to the 1/3. And since this is less than 1, this thing diverges. All these curves that where n is bigger than 1, they live above our border. Our border is 1 over x. Underneath this, you're finite. Above this, you're divergent. So diverge, converge if you live underneath there. But 1 over x is your cutoff line. Yes, ma'am?
So does that mean that any equation where it diverges, even if you'll have like a plus or a minus 2, like we had in that one example problem, the answer will always just be infinity?
Yep.
So we don't even have to.
That's right. That's right. Yeah, yeah. And then it'll show up a lot. And when we get to like the last 5-6 weeks of class, we'll be using this result in a very interesting way. But it's going to be one of our prime tools for knocking some stuff out. So that's all pretty chill. Let's look at one that doesn't quite fall into that bucket of problems. But I promise you I'll put some on the web work where you can just knock them out with this rule. But let's look at something a little more interesting. What about this one? What about integral from 0 to infinity of x e to the negative x dx. Let's work on this one together. So step 1, when you have an improper integral, is to make it a proper integral. Replace the infinity with a limit. Put the limit out front. And again, this is telling us, this is notation to help us ease things on our minds. Do this. Find that answer, then do this. That's what this is all meaning. Can you do this one for me, please? What rules do you, how would you do this integral?
Power rule? Or the one that pertains to E? Where
Yes, yeah. What technique of integration do we use to do x times e to the negative x?
Product.
By parts?
Parts, yes. So we got a product, so parts. So let's do this by parts. And then we'll worry about the limit together. But can you do that integral? first one is actually not, even though it looks like it should be.
It is not.
So don't take any limits yet until we talk, unless you're pretty solid on limits. That first limit is not trivial. Can I answer any questions on just like getting to where I'm at? Happy to clarify and make sure everybody's coming along. Feels like a million years ago that we did parts, even though it was like last week. I think we had an exam or something.
So, one over e to the negative b, the second one.
Where at point?
Underneath.
Underneath this?
Yeah. See where it's e to the negative b?
Yes.
Should it be 1 over e to the negative b?
No, it could be 1 over e to the b. So I could do that, and we can go ahead and do that. But it should be e to the positive b like that.
Okay.
Does that make sense, or?
Yeah.
Okay. Sophie?
Very good.
Okay, cool. All right, so I keep thinking, every time I keep looking up, I keep thinking,
Sorry.
it's all good. No, do what you're, you
I was
don't,
wearing a hat earlier.
don't stay, yeah, it's itchy, right? Like, yeah, hat itch. All right, so I'll take your word that you believe me on this. Some parts of this are easy. Well, that's one. So let's just grab the low-hanging fruit while we can. What does this one do as b goes to infinity?
Goes to infinity,
So the bottom does.
or it goes to 0.
Goes to 0. Okay, you had the right thought, just said the wrong things. So check it out. This one here is a fixed number 1 over e to an ever increasing exponent. So that's going to become 1. That's like 1 over infinity. That's 0. So this piece dies. This goes to 1. This is where things get interesting. Let's actually pull this over here for a minute. When you have a fraction and you want to analyze it, especially when you have an infinite limit like this, or a limit at infinity, notice that the top, b is going to infinity, and the bottom is also going to infinity. Top's blowing up, bottom's blowing up. Both pieces are moving. This is called an indefinite form. And that means it could be anything. When you have an infinity over an infinity, the answer could literally be anything. And let me prove that to you. What if I had like limit as x went to infinity of 7x over x? Now that's a cheesy answer, or cheesy problem, because you'd cancel the x's. And the answer's 7. But notice that the top is going to infinity and so is the bottom. But the limit is 7. However, if I had limit as x goes to infinity of 8x over x, that's also an infinity over infinity form, but the answer's 8. And I could literally make it anything I want just by putting that in front of the x there. You want it to be pi? Make it pi x over x. You're good to go. So these forms we have to be really careful with. That's the point. Does anybody remember how to deal with a limit where it's an infinity over infinity?
I remember.
Oh, is that the L'Hopital's rule?
Ooh, yeah, nice. Oh, yeah, L'Hopital bubbling up all over. That's good shit. So, L'Hopital's rule. The L'Hopital's rule is what you wish the quotient rule was, right? Derivative of the top, derivative of the bottom. There's no mixing. So I'm going to L'Hopital this. The limit is b goes to infinity. What's the derivative of the top with respect to b? 1, yep. And what's the bottom with respect to b? E to the b. So now it's easy to see. Fixed over blowing up. Where's it going? Where's this limit go? To 0. So that's why we gotta be careful, Becky, on that one. Yeah. Because the short answer, like the story is that e to the b blows up so much faster than b. That when b is like 10, you've got like 10 over, I don't know what e to the 10th is, but it's freaking huge. So this thing just keeps blowing up so much faster than the top that the ratio ends up just tending towards 0. So this goes to 0. And my final answer is -1, a +1, 1 unit squared. If you looked at the graph of this thing, it looks like this. So this is x e to the -x, and that's the area we just found. And it's infinite in size, but finite in volume. Let's just do one last thing and then call it a slightly early day. I would like you to do a volume for me. So let's take, because this will be part of a really cool math story too. So you guys are gonna write like the first chapter on it. Let's take 1 over x and all the way out to infinity. So we're gonna let x go from 1 to infinity. So I want this region. What is the volume of the shape formed by spinning that infinite region around the x-axis? It is not. We gotta do it. Let's crank it out. Let's do the formula, right? So what do we have here? Washers, shells? Washers, yeah. Little discs, yeah. So find the volume of this thing. This infinite horn that will be formed by rotating that around. Just use your classic, you know, the lowest hanging fruit of all the volume formulas. What is the volume? This is like so famous, it's got a name. It's called Gabriel's horn. So, nice. A lot of these really weird math things have fancy names. There's one called, a curve called the Witch of Ignacy, which is freaking awesome. If you like that kind of thing. Gabriel's horn has a kink in it there. What'd you get? Square. Yeah, but I'm just trying to get the square root. That's the part that's confusing. That's the right integral, definitely, with pi inverse. You like doing some inverse shit in your head, my friend?
So you just want us to find the integral, or?
Yeah, I want the whole volume. What's the volume? Yeah, find it for me.
Oh.
Yeah, you're almost there. Maybe. It's easy to do. Oh my gosh. You are. Yeah. Don't know. I would just like, that's just the power rule.
Oh, it is.
Because that's just 1 over x squared. So it's x to the -2nd. So like, you don't need to do all the subs.
That's just 1 over x squared.
That's just 1 over x squared. Yeah.
Oh, okay.
You're definitely making it too challenging.
Lovely.
Looks good. That is looking good. Let's see what we got. Okay, that I love that. got that. Okay, that's gorgeous. Yeah, it's cool. So like let's just take that infinity out real quick. Just scratch that out and put a limit as B goes to infinity in front. There you go. There you go. Yeah, yeah. But you got the right thing. That's it. That's it. How's it going, John? Yeah, beautiful. That's, yes. It's beautiful. Get a volume of pi units cubed, right? Finite volume, infinite shape, goes on forever. It's a finite volume. Is there any questions on getting that volume? Everybody looked like they were cruising in the right direction, so that was really awesome. So I want to tell you something. I'm not going to prove it. Maybe I'll show you on Friday. I'll write it up. But we can compute the surface area of this thing too. And I'll talk about that on Friday. Or maybe I'll do a little quick write-up so we can see it fast. But I can find the surface area of Gabriel's horn. It turns out to be infinite. So it turns out the surface area is infinite. So infinite surface area. Finite volume. So one of the great paradoxes of math is this, Gabriel's horn. Because if it's basically a paint can that can't hold enough paint to paint itself. So I can fill this with pi liters of paint, but I can't paint it. The surface area is infinite. Just insane. Yes, Abraham.
Does that go for like all shapes made this way with the finite
Not
volume?
necessarily, yeah. No, this one's got a special nature. It's at 1/x. Like if we had made a, if the outer curve had been maybe like 1/x squared. In fact, I'll work that through. I think it would have finite surface area then. But this beast has can't hold enough paint to paint itself. Now, that's just a weird way to say some things, because surface area and volume should not be compared. They're just really weird, different things. And then let's just keep in mind, this is all just made up, right? This isn't real. Well, like, how could you even fill this with paint? Because eventually, the paint molecules aren't going to go to the bottom anyway, right? At some point, this becomes so tiny, it's not even the width of an atom. So the things that just lodge. I mean, let's not even think about viscosity and all the things that would actually be going on with that. But it's kind of a cool paradox of math.
So you wouldn't even be able to blow Gabriel's horn, it's just too thin for air to
That's
go through.
right, that's right. Yeah, only an angel could possibly do that, get sound out of that beast. Alrighty friends, let's call it there today. So, Zoom class on Friday. Again, bonus for showing up, keep the video on. I've got all those. I haven't put them in the grade book, but they are there, and they will be there for midterm. Gabe, would you mind hitting that?
Yeah, of course.
Thank you, sir.